Good morning. Happy Friday. I hope your day is going okay. We're going to start a review today for the first midterm. We'll talk about that here in a little bit. But today, for those of you in section 01 at 110, when we meet in 2501, turn in the valence bond molecular orbital lab. Problem set number 3 is up. Now, problem set number 3 is, of course, all OChem. Quiz 3 will have OChem as well as a molecular orbital question. So that's a little bit of an unusual twist, but just realize that. And then the lab today will be the organic chemistry lab, where we'll go around. For what it's worth, next week's lab, we're back in the lab. And I need you to bring goggles and stuff like that. Pretty fun lab, so get ready. But this Friday, another paper lab, ask questions, stuff like that. Any questions on that? Not this week, of course, but next week we'll tackle the first midterm for Chem 222. And the first midterm will be over chapters 7, 8, and 20. So 7 was Lewis structures, how to build them, formal charges, as well as Vesper geometry, EPG, MG, polarity, stuff like that. Chapter 8 was basically valence bond and molecular orbital theory, how they work, where we are with them. And then, of course, chapter 20 is the OChem chapter. Now, normally in a midterm, I have kind of equal questions over all 3 chapters, but this exam will be more over chapter 7 and 8. You will see some OChem, but it won't be as much as the other 2, so just keep that in the back of your mind. When you come to lab next week, Friday or Wednesday, here's some things you should bring. There's one kind of question where you do need a calculator. It's the bonds broken minus bonds formed things from chapter 7. So do bring a calculator. You won't need it very much, but it will be helpful to you on that question. And I do recommend you bring a pencil. You are definitely welcome to bring a notes sheet, staple it to the back when you're done. You'll bring the completed organic chemistry lab that will start today. Exam prep 1 will be due next Friday. Now, if you're new to my world, an exam prep is just a series of questions, usually about 5, where I give you the question, I give you the answer, and you just show your work how to go from the question to the answer. And the first one of these will be due next week, Friday. Exam preps are things that if you get to number 3 and you're like, what the, all right, reach out to me, all right, reach out to the tutors, because I want everybody to know how to do these problems before you go into the actual exam. So that'll be next Friday at 1 o'clock. And then you need to bring a printed copy of the next week's lab, the molar mass of a volatile liquid. Now, this is a fun lab. Out of all the labs in 221 through 223, this might be my favorite. Inside your email. Molar mass volatile liquid is pretty cool. You do need safety goggles. This one, mandatory, absolutely. I have some you can borrow. You're welcome to use mine if you want, but of course, if you have your own, it's maybe not as nasty, blah, blah, blah. So bring some safety goggles. The midterm itself will have 20 multiple choice questions and 5 short answer questions. It'll go about 2 hours. So like if you start at 1:10, it'll be done at 3 o'clock. If you are new to my world and you haven't seen an exam, there is a sample exam both in the companion and online. And I do recommend you check it out. I give you the answers to that exam so you can practice and stuff and see what's happening. Definitely check that out. But anyway, you'll take the exam for section 01 next Friday, and then the following Friday, I'll return the exam to you when I return your other stuff. When you get it back, you'll have a summary sheet. I'll staple it to the back. And the summary sheet is just how you're doing in the class as of this time, if I had to give you a grade and stuff. So you can check that out and make sure that what you have turned in is what you actually got. I didn't misput your grades in and stuff like that. Today and Monday, we'll do some review and stuff just to give you some examples of questions you might see. Are there any questions right now? Let's do this then. So what we'll do is we'll just go through a whole series of questions. If you have an iClicker, you can use it, but if you don't, just think about what the answers should be, and we'll go from there. So anyway, this is a Lewis structure question, and it says, which of the following is not a correct Lewis dot structure? So see if you can figure out which of those isn't a correct Lewis dot structure. And we'll talk about it here a little bit. So this question is a great segue into reminding us about what Lewis structures are all about and stuff like that. If you don't see this, which is totally cool, let's just review real fast how you would first draw a Lewis structure. So the first thing, good old count up valence electrons, hydrogen in group 1, so 1 valence, carbon's in 4, nitrogen's in 5. So HCN, answer B, would have 10 valence electrons. I usually divide them by 2 because we deal with pairs most of the time, 5 pairs. Now the central atom cannot be hydrogen, all right? Hydrogen can only handle 1 bond. Hydrogen's listed here because this is a type of an acid, all right? So we're not gonna have hydrogen. Between carbon and nitrogen, the least electronegative element will be in the middle. And generally speaking, as you get farther from fluorine, the most electronegative, you get less and less electronegative. So carbon is the least electronegative of all of those there. We're gonna put carbon in the middle. And we have to connect those atoms together. And by drawing each of those lines, each of those is a bonding pair. So I've drawn 2, I've used up 2 of my 5 pairs. I have 3 pairs left. Now, the outer atoms get lone pairs first, and if there's anything left over, put them in the middle. So I'm gonna give this nitrogen an octet. And again, an octet means 4 pairs. At least the outer atoms will be electron happy, if you will. And that's what we have. But before you move on, you've got to see if the central atom is quote-unquote happy as well. Does it have an octet? Does it have a formal charge of 0 if possible? And so in this case, carbon only has 2 pairs. And as we've talked about so much, carbon has to have 4 pairs. So I'm going to make not just a double bond, I'm going to make a triple bond there with HCN. So that's the Lewis structure for HCN, and HCN obviously up there looks the same. So the thing is not HCN, but this is a great talking about how to make a Lewis structure. Questions on this part? Okay, good. Now, let's do NO minus, which would be the one in the lower left corner. Now, nitrogen, again, valence electrons 5, oxygen is 6. Minus 1, does that mean add an electron or take away an electron? Add, that's right. To have a negative means to add. It's the opposite of money. I don't have any dollar bills. I'm sorry, I can't tell you right now. But anyway, brought that back on. This would be 12 valence electrons or 6 pairs, okay? Now, for N and O, there's really no central atom, so just put them next to each other, connect them. Between oxygen and nitrogen, I would put them on the oxygen first. It's more electronegative, more into atoms. So octet means that. I now have 4 pairs around it. I've got 2 left. I'll put them on the nitrogen. So if I need to have nitrogen have an octet, which it does need, i.e. 4 bonds, I'm going to make a double bond. Would we have a triple bond? No. In this case, that is not NO minus, that is NO plus, all right? And you kind of have to go through a Lewis structure like we just did to see it. NO minus is a double bond with each N and O has lone pairs on it. But NO plus, which is really what we're seeing there, is a triple bond between it. So the charge here was deceiving. Those are the kind of things. Most of these kind of questions, it'll ask for octet, like it'll give you carbon with only 3 bonds or something, and that would be bad. But if you don't see that, like all of these have 4 bonds around them except for hydrogen, which doesn't need it, then the next thing to look for is usually the charge. Like either they'll add one when you should subtract or vice versa. So, any questions? So here's another one. Which one of these now is not a correct Lewis dot structure? See if you can figure out which of these is not correct. Excellent. People seem to be rocking this. Okay, so on this one, all of these are neutral compounds, so we don't have the positive, negative thing like we saw earlier. But what you can do is try to make sure that hydrogen only has one bond, carbon, oxygens, 4 bonds, et cetera, et cetera. So for example, here, this is formaldehyde. Carbon has 1, 2, 3, 4 bonding pairs, so 4 pairs makes carbon happy. This would also have a formal charge of 0. Oxygen, as we've talked about, oxygen likes to have either a double bond and 2 lone pairs, or a two single bonds and 2 lone pairs to make it happy. And this is definitely happy oxygen. All right, anytime you've got a double bond and 2 lone pairs, formal charges are 0. This molecule looks really good. Chlorine is a halogen. Chlorine likes, and all the halogens like to have 3 lone pairs and a bonding pair if they're on the outside. Excellent. Nitrogen, 1, 2, 3 bonding pairs and a lone pair, so that's it's 4 pairs. It's happy. Now, it may seem at first like this is a possibility, all right, because oxygen here, this is a happy oxygen, 2 bonds, 2 lone pairs, and this oxygen is happy, 2 bonds, 2 lone pairs. But this one right here has 3 lone pairs and a bond. What would be the formal charge on that oxygen right there if you figured it out?
-1.
-1, outstanding. So at first this might be a red flag saying, that oxygen's funny. But if you look at the nitrogen here, nitrogen in group 5, all right, nitrogen 5, it's got 1, 2, 3, 4 pairs around it. Now, nitrogen has a formal charge of 0 when it has a lone pair and 3 bonding pairs. This is definitely not that kind of nitrogen. However, in this structure, if you remember from the Lewis Structures lab, this is actually a good structure for HNO3. It's got a positive nitrogen and a negative oxygen. You can resonate the molecule so it goes around, the double bond goes down. This is actually okay. The overall formal charges of everything go to 0, and that usually means it's pretty stable. But if you look at D, and I think everybody was seeing this, the middle nitrogen here is not a possibility. Now, we talked a lot in this class about atoms that can go beyond an octet, but those are period 3 and lower. So for example, phosphorus right below it, it can make 5 bonds. But nitrogen, carbon, oxygen, fluorine, etc., limited to 4. So this nitrogen has 1, 2, 3, 4, 5 bonds around it. That would be a forbidden thing. The 2s2p configuration of nitrogen doesn't have a 2d orbital set to pull upon. And so that would be an unusual structure, let's put it down. Any questions? Formal charges are important. They help you to find what the most stable configuration of resonance form will be. See if you can figure out what all the resonance, thanks for playing, what all the formal charges are on the formate ion. Now, formate ion does resonate, that's what I was trying to get across, but if this was the stable structure, see if you can figure out what the values are.
With the bond order for that carbon be like 4s?
So the carbon-oxygen bond order, Clifford, you would take the total number of bonds. So there's a double on the left and a single on the right, so 3, okay? And you divide that by the number of places those could go. So there's the left and the right. So I would say the bond order of CO here is 3 halves, all right? It's a resonating bond order, so that's why it's a little weird. If it was 4/3, you could, like carbonate, you'd have another oxygen where the hydrogen was. But we don't have that in this case and stuff. So.
I look at the oxygen carbon chain.
Mm-hmm. Yeah, that's right. Good. Excellent. Everybody's rocking this question. Well done. Officially, formal charge, group number minus lone pair electrons minus half the bonding pair electrons, or you can just take group number minus the number of bonds minus the lone pair electrons. Definitely count each lone pair electron. So this would be 2, 4, 6. Don't make them, but you only do the individual bonds. And what everybody was figuring out, which is really cool, 0, 0, and -1. Carbon has 1, 2, 3, 4, and that's what it wants, so it's 0. Oxygen, 2 lone pairs, 2 bonding pairs, so 6 minus 4 minus 2 is 0. But this oxygen, 6 minus 6 minus 1 is -1. Something has to be -1. The formate ion has a charge. So you don't want to have everything be 0, but in this case, that's going to be there. Now, Clifford was just asking about the bond order, which is cool. This is a fairly stable ion because the double bond here could be on this side as well. So that negative charge, which is what we see in the formal charge right there, can go back and forth, and that tends to make the molecule a little bit more stable. So, any questions? Sweet. All right, lots and lots of geometry kind of stuff on this midterm, so just get ready. So let's say you wanted to know what the molecular shape or molecular geometry of sulfur dichloride is. What I would do is first draw the Lewis structure and then apply Vesper geometry to see what's going on. So see if you can figure out which of those would be the molecular shape or molecular geometry of SCO2. Cool. So SCl2, same game like before. Count of valence electrons, sulfur is 6, chlorine is 7, and there's 2 of them. 14 plus 6 is 20, divided by 2, 10 pairs. Central atom, usually the first one listed, not hydrogen. This is hydrogen, so let's put sulfur in the middle, chlorine is on the outside. Got 10 pairs, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Bam, Lewis structure, woohoo! Any questions how I got to that? Okay, now comes the Vesper part, all right? Vesper's all about keeping those lone pairs as far apart from each other as they can. When you draw it, it looks like the CLs are 180 degrees apart from each other. And if there were only CLs, that's where they'd want to be. Far apart, you can get them, the better. But how would we describe the electron pair geometry of that sulfur? Tetrahedral. Yeah, tetrahedral. And tetrahedral isn't 180 and 90 degrees. It's 109. So that's why sometimes you see, Clifford did it better with his hands there than I could do. But yeah, it's not like a 90 degrees and 180. It's actually 109. Now, my art skills are horrible. But if I was to try and draw this, it would be something like that, all right? It's not 180 degrees apart from each other. Go ahead.
It kind of looks like the tripod, right? Tetra? Or, no?
Yes.
That's what tetra is, right?
For those of you in my video audience, I can't show you the tripod really without doing it, but the tripod is like a tetrahedral. You're right, that would be a closer representation. Dude, that's pretty cool, you saw that. Anyway, all right, prop that back on. So, it's not linear, all right? EPG would be tetrahedral. 1, 2, 3, 4 clouds want to be as far apart as possible. 109 is better than 180s and 90s, which you'd have in a linear. Now, if you have tetrahedral and two lone pairs, then the molecular geometry, which again is going to be something like that, is referred to as bent. All right. So here's the Vesper Lewis structure, and again, Lewis structures don't have anything to do with actual geometry. You have to interpret that and make it in your mind something like that. Okay. So it is a bent molecular geometry. Tetrahedral with two lone pairs is bent. It's like water, things like that. So, any questions? Orthorhombic is something we'll talk about after the first midterm. So you'll see that term again, but not right now. Okay, here's another one. IF2 minus 1. See if you can figure out what its molecular geometry is. So I would draw a Lewis structure and then interpret the Lewis structure for Vesper rules. Yeah.
Do I need to register my clicker again this term? Or you had it last term?
If you look at your grades on my website and under iClicker register, it says yes, you're good to go. If it doesn't say yes, then talk to me and we'll do it. Did we do yours manually last time? I can't remember. Okay. Check. If it says registered, then you're good, but if it doesn't, just send me your iClicker. Okay. So up here on the board, I put the Lewis structure for IF2 minus 1. The iodine has 2 bonds to fluorine, but it also has 3 lone pairs around it. So the question is, how do we describe the geometry? This is kind of a trigonal bipyramid right here. When you have 5 pieces, 3 lone pairs and 2 bonding pairs, they're going to be around in a 5-coordinate system, which is the trigonal bipyramid. And there's a couple different possibilities you can do. Now, first of all, you could just look in the geometry and polarity guide and get the answer, which is awesome. If you want to think about it though, the lone pairs, I was talking with someone recently, lone pairs are kind of like a storm. And you want to keep the storm as far away from the atoms and other storms as possible. But if you have 2 storms, you want to keep them definitely as far apart from each other as you can, because when storms combine, it gets bad. I don't know if that works for you, but I thought it was kind of an interesting question. Now, atoms like fluorine have protons to hold on to their electrons. But electrons, as a lone pair, it literally is like a storm. It takes up more volume. And that's big negative energy. So why that's important is because in the trigonal bipyramid, you have three angle choices. You've got 180 above and below. You have some 90-degree orientations. So like these kind of angles would be 90. And then in the plane itself, you have 120. Now, if we had two lone pairs, we'd try to put them like above and below, because that would keep those storms as far apart from each other as they can. But we have three of these lone pairs. So to keep them as far apart from each other as they can, they put them in the middle. They call it equatorial sometimes, axis. And that keeps those storms at 120 degrees from each other. Having even one lone pair at 90 degrees from another lone pair is really bad for a molecule. Think of it again as those storms are getting too close to each other. So in this molecule, what happens is the fluorines go in the up and down positions, all right, the axial positions. Don't worry about that. But the really interesting thing then is that this molecule, this IF2 minus, ends up with a linear molecular geometry. The FIF angle is 180 degrees. You're trying to keep those lone pairs, again, as far apart from each other as you can. This is actually a non-polar molecule. The F's cancel out, the lone pairs, everything around that, and the trigonal planar is the same. It's kind of a bizarre phenomena that happens with these trigonal bipyramids with three lone pairs. So I'm just introducing it here to make you think a little bit more about it. It looks like people were doing a good job. Any questions? Acetylene is a molecule that we're going to talk about today. Acetylene is also known as ethyne. And I'd like you to try and figure out what the approximate carbon-carbon hydrogen bond angle is. So you can draw the Lewis structure for C2H2 if you don't know what it is. If you do know what it is, you can figure out what the bond order is going to be. See if you can figure out which of those would be a great bond angle for C2H2. So up here on the board, I have a partial Lewis structure. All right, I counted the valence electrons for C2H2. It came out to be 10 or 5 pairs. You then put a bonding pair between the atoms to keep them all like in line. That's 3. I've got 2 left, so I put 1 lone pair off each carbon. Now, carbon almost never has lone pairs. I'm not going to say never, because you will see some weird things with it once in a while. But if you see carbon with a lone pair, you've got to do something with it. All right, in Chem 222, we're not going to see any examples of carbons with lone pairs. So with this structure, hopefully a warning goes off, says, something's wrong. And the something wrong is because carbon must have 4 bonds. That's carbon's mantra, all right? So right now, each carbon has 3. And that's not cool. So let's take away that one and make a double bond. So that actually gives this carbon 1, 2, 3, 4 bonds, which is happy. But this carbon still has 3. So let's take away that one too and make a triple bond. That will give all the atoms an octet. Hydrogen just needs 1, stuff like that. All right. Double, triple bonds count as one cloud, just like single bonds and lone pairs. So around this carbon, this is a cloud, this is a cloud, 2 clouds, far away from each other as they can. That would be 180 degrees. This is a linear VPG, all right? This is literally like right across right there. Triple bonds, like in ethine or acetylene, which is the common name, have a lot of energy on, and that's why they use acetylene for torches and stuff, because a lot of energy is given off. But the important part is, yeah, these molecules are truly linear and stuff when they're made. Questions? Sweet. All right. Electronegativity helps us to figure out what atom goes in the middle of a Lewis structure. And the most electronegatives are usually on the outside. So see if you can put these in order of increasing electronegativity. So from least polar to the most polar. And answer E has a special message for you. I saw this on a chat room one day, and I don't get to talk about Presdorium a lot, but anyway, woohoo, part of the surprise. Anyway, dork alert. Anyway, electronegativity, fluorine's the most electronegative, everything farther away from it. Generally speaking, electronegativity goes up and to the right on the periodic table. And what everybody saw, which was fantastic, magnesium is most on the left. You go to the right to phosphorus, then you go up to nitrogen, and right to fluorine. Fluorine's the most electronegative and stuff. Nice job. Any questions except for on my bad sense of humor? Formaldehyde is an example of an aldehyde. The formal name of formaldehyde is methanal, but if you didn't know it, you could figure out the Lewis structure for formaldehyde / methanal and think about what the bond order is for the carbon-oxygen. So see if you can, by hook or by crook, figure out what the carbon-oxygen bond order is in formaldehyde. So up here on the board, I have a partial Lewis structure. I found the valence electrons, number of pairs. I connected the outer atoms to the middle, which is almost always carbon. That took up 3 of the 6 pairs. The other 3 would go around the oxygen initially. But before you're done with this structure, you should see if the central atom has 4 pairs, and it does not. It has 3 right now. So in order to make carbon happy again, you've got to give it the 4th pair. So this compound, formaldehyde, has a carbon-oxygen double bond. And anytime you see a double bond, the bond order will be 2. So this carbon-oxygen would have a bond order of 2, okay? Aldehydes and ketones will always have carbon-oxygen bond orders of 2. Alcohols and ethers will have bond orders of 1. They'll got oxygen with 2 bonds and 2 lone pairs and stuff like that, so. But on the other hand, you're always welcome to just draw the Lewis structure. Now, bond order, pretty important to chemists, because as bond order goes up, your bond energy goes up. So I made Clifford do like shake hands and all that jazz, and a double handshake was harder to break up than like a single handshake. On the other hand, as bond order goes up, your bond length goes down. Clifford, I'm so glad to see you. I'll move closer to him, all right? And that's kind of what atoms do with these kind of things. So. Question? Formate, we saw earlier, was HCO2 minus 1. If you remember the structure, cool. If you have your notes, you can look back in it. But either way, see if you can figure out the bond order of formate. Formate will resonate. So it's a little bit different kind of a bond order. So see if you can figure out what's going on. Outstanding. So on this structure, this is the partial Lewis structure. I got to this point. The oxygens have octet, hydrogen only needs 1, so it's happy. But as most of you saw, yeah, carbon is not happy. Carbon right now has 3 pairs and it wants to have 4. So on this molecule, you could take a lone pair from that oxygen and make a double bond right there. But there's really no reason why you couldn't take, say, one of these lone pairs on this oxygen and make a double bond. Excuse me, right there. So this is a molecule that resonates. All right, you have a choice of where the double bond goes. Now in resonance, you freeze the atoms. All right, you're not rotating or anything like that. You're freezing the atoms. And if you have a choice where the double bond goes, that's when you're going to get into resonance. Now, to figure out the bond order of a resonating structure, you take the total number of bonds involved in the resonance. So here, this, and this, those are the 3 bonds that are associated with resonance. And those 3 bonds have 2 places they can go. There's 2 carbon-oxygen lengths. So I would say here that the bond order is 3/2 or 1.5, all right? And that's just one way to show how it is. In reality, you don't have a double or a single. You have a mixture. It's more than a single, but less than a double. All right, that's what it's trying to say. So it's more like a 1.5 bond. And so sometimes you'll see people drawing little dots like that right there. I don't really like that, but that's the best way sometimes you could do these kind of things. It's better just to know that resonance happens. And if you see one of these weird fractional bond orders, that's totally what it's telling you. It's saying, hey, wake up. This isn't a double or a single. You've got a resonating structures. All right. This is the one kind of question where you're gonna need a calculator. If you have your calculator, you totally can get it out and work on it. If you don't, I'll just talk about the answer. But this is a question when you have bond dissociation energies, all right? So these numbers right here, always positive numbers, it's the energy required to break apart those bonds. So in a question like this, if I said find the bond dissociation energy for this reaction, you would take the bonds broken minus the bonds that form. So in this case, that would be, you take the bonds of the reactants, because those are the ones you're breaking, and subtract from it the bonds that you're forming. Along the way, you'll probably have to do some Lewis structures just to see what kinds of bonds you have. You might be able to figure out what these are without doing Lewis structures. Either way, bonds broken minus bonds formed, bonds reactants minus bonds products. See if you can get one of these answers done. Cool. So a couple of things about these kind of problems. First of all, you never have to memorize or know or put on your sheet of notes, these kind of stuff. I would absolutely give you those. These numbers are always positive because once you make a bond, to break it up, it takes energy, so they're endothermic, blah, blah, blah. When you're doing these problems, there's two important concepts to remember. Sometimes the reactions as given will have weird stoichiometries, i.e. non-1, all right? So notice that there's a 1/2 there and a 3/2 there. We only really need one nitrogen in the product. This is a heat of formation we talked about in Chem 221. So that's why there's a 1/2 there. And because fluorine's a diatomic like nitrogen, we only need 3 fluorines. We don't need 6 of them. So that's why there's the weird fractions there. I would have to use fractions on this problem because it's one of those stupid formation things. Oops, Prof. Ad fell off there for a little bit. So that's one thing. Make sure you pay attention to the stoichiometries. The other thing is that in NF3, you have one NF bond here, a second NF bond here, and a third NF bond here, all right? So bonds broken minus bonds formed. Bonds broken, 1/2 of whatever the triple bond N is, plus 3/2 whatever the FF bond is. That's the bonds broken part. And then you'll subtract from it the bonds that you form. But in NF3, you don't have one NF, you actually have 3 NFs. So you take 3 times this number because you have 3 NF bonds. So anyway, if you did all this correctly, minus 105 is what you're looking for. So you can see here, here's my 1/2 times the 946, the triple bond, and 3/2 or 1.5 times the 159 for the FF bond. But then bonds broken minus bonds formed, notice how I multiplied the NF bond by 3 because this has 3 NF bonds in it. So you'll have one of these kind of problems. They're not hard. I'll give you these numbers. You just need to put in bonds broken minus bonds formed. Look at the stoichiometries, look for the number of bonds. Questions on that? I think I have time for one more question because this one's really fast. It says, which of the following bonds is least polar? All right. Least polar honestly just means that your 2 atoms would be really close to each other. AC/DC, unfortunately, is not a chemical bond, although I like them a lot. So in this case, all of them have boron. You just want the element which is closest to boron. That's going to be boron and carbon. That would be the least polar. If you had a boron-boron bond, that would be even less polar, but in this case, they're all different ones. Questions? All right, we'll do more of this on Monday. I'll see most of you at 1 o'clock today in 2501. Have a great day.